industrial programmable logic controllers, high-speed thermal sensors, and modern solid-state drives each rely on structurally different electrical architectures. If every piece of hardware requires its own electrical language, writing control software to link them together means writing and maintaining distinct custom device drivers for every single permutation of hardware. This photograph of an early IBM machine shows how hardware routing used to be handled. Moving data from one component to another meant the connections had to be physically rewired by hand. Linux resolves this hardware chaos through a strict engineering mandate derived from the original Unix philosophy. Everything is a file. In practice, that mandate allows an engineer to route physical sensor data using a single shell command, cat, pipe, grep, redirect to a log file. The first component of this syntax reads the raw data streaming in from a physical serial sensor on the manufacturing floor. The middle component takes that data and filters it in real time, isolating only the lines containing an error state. The final component captures those isolated error logs and writes them to persistent disk storage. This one line of text replaces hundreds of lines of complex, hardware-specific driver code. By reverse engineering how the kernel executes this command, we expose the mechanical architecture of the Linux Universal I/O model. A strict boundary separates user space, where applications run, from kernel space, where the system interacts with physical hardware. To cross it, Linux relies on the POSIX Universal I/O standard: open, read, write, and close. Applications cannot communicate with hardware directly, issuing only these 4 calls to the kernel. The open call sets connection terms, passing the file path and flags that dictate exactly how the kernel handles data. For example, appending the OSync flag forces the kernel to write data synchronously to the disk. The call waits for the physical disk to confirm the write before returning, preventing data corruption in the event of an industrial power failure. Once the connection is established, read and write operate as agnostic byte pushers. They are blind to whether the hardware is a high-speed solid-state drive or a thermal sensor. Finally, close severs the connection and releases the kernel resources assigned to that operation. This 4-function API forces all hardware to behave identically from the software's perspective. The application requires no specific hardware logic to function. The phrase, "everything is a file," is a misnomer. In Linux, everything is a file descriptor. When an application calls open, the kernel executes a C function called getUnusedFD. If the open call is successful, the kernel simply returns a non-negative integer back to the user application. The application receives an integer, indexing the process file descriptor table. This points to the system-wide file table, tracking access modes across the OS. Finally, the pointer routes to the Inode table, which describes the actual physical hardware device. Opening a device triggers the filp_open and fd_install kernel functions, executing this exact mapping chain in a fraction of a millisecond. For all subsequent read or write operations, the application does not submit a file path. It simply hands that integer back to the kernel. This triple table architecture isolates the application from the hardware. The immense complexity of physical device management is hidden entirely behind a single integer. Returning to our original command, the first file path is /dev/ttyacm0. This is a special device file. It does not exist as stored text on a hard drive. It represents a physical port. A character device, like a serial port, streams data sequentially, unbuffered, for immediate real-time reactions. A block device, like an ext4 solid-state drive, operates differently, collecting and moving data in fixed, structured chunks. Block devices utilize dual-layer buffering across the C library and the kernel. To optimize performance, the kernel waits until exactly 4,096 bytes are collected, matching the ext4 file system block size, before executing the physical write. Character streams are unbuffered and real-time. Block storage is buffered and rigid. The I/O model handles both invisibly. When an application launches, the kernel automatically assigns it 3 inherited standard streams: standard input at 0, standard output at 1, and standard error at 2. This Western Union teletype machine shows the origin of these streams. Legacy standard input was a physical keyboard, and standard output was punched paper tape. In our shell command, the 2 right-facing arrows represent append redirection. Shell redirection intrasets standard output. detaching the pointer from the terminal and snapping it directly to a log file. The pipe symbol creates an anonymous pipe between two concurrent applications, linking File Descriptor 1 of the first directly into File Descriptor 0 of the second. Because an anonymous pipe moves data entirely within system RAM, the kernel bypasses the physical disk, removing the latency of mechanical writes. Standard streams and pipes allow engineers to snap modular, single-purpose programs together. Complex data pipelines can be composed dynamically without writing new integration software. Data flows out of the physical character device, moves through the RAM pipe into the text filter, and is synchronously written to the block device. A philosophy developed for early mainframes successfully controls the electrical signals of modern embedded controllers and manufacturing sensors. This architectural diagram shows a modern scaling problem. Standard POSIX calls are blocking, meaning the application must wait for the hardware to respond. When industrial systems need to process millions of events per second, this creates severe bottlenecks, driving the development of advanced asynchronous APIs like IO-Uring. While advanced APIs like IO-Uring represent the next stage of I/O performance, the file descriptor remains the primary mechanism